Hey, welcome to Ones and Zeros. My name's Ben, and in this video, we're going to be taking a bit of a look at one of the uses that there is for the timer peripheral in STM32 devices. So, I'm going to be doing a set of different videos where we look at some of the different ways that timers can be used because they are pretty flexible peripherals. Today, in this video, we're going to be looking at using the update interrupt request for timers so that we can use a timer to trigger a specific set of instructions or a bit of code to run at a particular interval, and going to be doing it so that we can either get it to run continuously if we want it to be something that's always running, or if we want it to say run 4 or 5 times or 10 times or something like that and then stop, then we'll be able to do that as well. And much like we've been doing with a lot of our videos, we'll be doing it as a class so that we can actually reuse that class for multiple different timers. And this is kind of following on from our previous stream, which I finished about an hour ago, where we actually created a dynamic timer manager class, which is able to keep track of what timers are actually in use and what they're being used for, whether they're available, what features they support, all that sort of stuff. So I'd recommend checking that one out because we will be using some of that stuff in this video. And much like our previous couple of STM32 basics videos, the code from this video will be available on GitHub shortly after the stream is finished as well. So I'll make sure to drop a link with the video there. So let's jump into it. We're going to be using our F411 Nucleo device for this one as well. And this particular device has 8 timers, so we're going to be seeing how we can leverage those in different ways over the coming videos. So there's 8 timers, as I mentioned. There's 2 32-bit timers, the other 6 are 16-bit timers. 5 of the different timers have encoder support, which we're going to be taking a look at in the next video. But let's get stuck into some code and we will see how we can use the timer update interrupt to make some things happen in this video. So all of this code, again, following on from the previous stream, which is also the same code that we use to do the external interrupts video as well. So kind of adding to that as we go. So you can see all of the stuff we've added to it so far. And add a header file and a source file for our driver for our update IRQ. And just going to call this one Q8E timer. This is kind of what I think is the most basic use for a timer for these devices. Copy and paste our header for that one and get that one fixed up. So a few different things that we're going to be looking at with timers over the coming videos. So the using encoders will be the next one that we come out with. I believe it's now the 19th. Came the 19th about 20 minutes ago. At least here where I'm in Australia anyway. So yeah, the next one will be encoders, and then we're also going to be doing one following that on pulse width modulation. There will be a few other different ones that will be coming out in future with timers as well. We'll also be making use of the timers in our ADC video, which will be coming out probably after the pulse width modulation one, where we'll be using the timers to trigger the analog to digital conversions at a regular interval. So they'll be making use of the timer manager that we did in the last stream as well. So let's get make sure I've got all of that right. Let's get our CPP file sorted while we're here. Get rid of this guy. We want to include our QED timer HPP, and we'll get rid of this bit here as well. All right, now we are going to just pop in an enum first up so that we can keep track of what mode the timer's in, whether we want it to run continuously or a set number of times. So let's call that timer mode. And timer continuous or timer brain's not working. Might just call that multiple. We might add one to single as well, just if we want it just to happen once. And let's get our QED timer class set up in here. Third stream for the evening. My brain is not working as well as it was for the previous couple. Get a bit more coffee happening, that will sort that problem out. Also going to want an initialization structure for this as well, so let's pop that in there. Type dev struct and QED timer struct, like so. Now let's get an enum in here as well, which you may have seen me use in previous videos, just so that we can set it up to either do a partial or a full deinitialization, so that if we get partway through the initialization of the peripheral and it fails partway, then we will only partially deinitialize it. Otherwise, we will tell it that we want to do a full deinitialization. So that's what we're going to use that for. We're going to pop in which timer we're actually going to be using so we can keep track of that. And for that one, also going to need to include our timer manager in here as well. So all of that stuff from the last stream, we've got the different timers for our F4 device in there so that we can tell it which one we want to be using. So I've got that guy there. We also want a handle for that one. We want to keep track of what mode it's in, whether it's in continuous, multiple, or single. We want to keep track of what the prescaler is for that one. And the period. And we use a uint32t for those to allow us to either use a 32-bit or 16-bit timer. That way it's going to work fine for both. Store what our IRQ priority is going to be for our update IRQ. I want to keep track of whether or not we have initialized this one or not. And whether or not it is actually active. I believe we have already popped those into setup. Yep, cool. And then we've also added a couple of other results into here, into our setup during the last stream, just so that we can return whether or not the peripheral is busy, so that if we try to set up 2 timers, so set up say timer 2, and then we try and set up timer 2 again, it can return saying that the peripheral is busy. And then we've also added one for peripheral not supported. So in a situation where, say in the next stream, where we are going to use encoders, if we try to set up an encoder using a timer that doesn't have encoder support, then it'll be able to return the specific error for that one as well. And as I mentioned in the last stream, we will be adding to that as we go as well, different errors and things, so that when we get to the point where we're actually doing a particular error manager, so that we can handle, you know, failures and things like that nice and gracefully, we'll have that ready to go as well. Now we're going to use the callback function and callback class much as we did for our external interrupt video, just to give us a bit of flexibility as to whether we want to use just a standalone function or a class. And the benefit of the class is that we can use it as a class that we can inherit from. So we can embed that as part of another class and then be able to call that, the handler function in that class, at the point where the timer update is actually triggered, which is something that we will make use of moving forward as well. And lastly, we're going to keep track of, for our multiple mode, how many times we want it to trigger before it stops. So we'll have our target amount that we want there, as well as where it is actually up to with that, which will be our counter value. So that's those guys. Now in our init struct, a few of these in here as well. So we're going to need our, what our peripheral is, what mode we want to use, what our prescaler and our period is, and we'll also pop our priority in there as well. We might also pop our counter target in there as well, so that we can supply that all in one go, like that. Now, because we're going to want to supply that initialization structure to the class when it gets constructed, we are going to remove our default constructor. So this QAD timer equals delete, and then I'm going to create a constructor that receives a reference to our init structure, and go through and do our member initializer list. So it'll be sinit e timer, ms handle, just fill that guy with zeros. Now me mode, that will come from our init structure. Want our prescaler, which also comes from our init structure. Our period. Our IRQ priority. It's always good to do the initializer list in the same order as we've declared the variables in the class as well, just because it does help when you come back to it at a later date. So me init state will be QA not initialized. me active state will be QA inactive. Now, not going to set our IRQ in there. However, we will do our handlers, which will be null. Now, counter target, which will come from our init structure. Might rename that in the init structure because that should be target rather than value. Like so. And lastly, we'll do our counter value, which we'll set to 0 initially. And that should be all we need there. Looks like the stream is behaving itself, which is always good. And we're also going to pop a destructor in here so that it stops and deinitializes the timer in the case where we destroy the class. So let's pop these in because I know what I'm going to call the functions for those anyway, which will be stop. Actually, that'll be, let's rename this one. I'm just going to call this state. Fix that up here. And for the particular use that we're going to use the timer for in this instance, there's two main bits of data that we need for the timer peripheral, which is the prescaler and the period. So in the case of the 8 timers in this particular device, they're all going to be running at 100 megahertz. So the 4 of the timers are connected to APB2, or the peripheral bus 2, which is running at 100 megahertz. So they get their clock directly from that. The other 4 are running off peripheral bus 1, or APB1, which is running at 50 megahertz. However, that 50 megahertz is being clock doubled and then being supplied to those 4 timers. So effectively all 8 timers, regardless of which bus they're on, are getting 100 megahertz clock with the way we've set the clocks up in this case. We did talk about that a little more in the previous stream, but going back to our prescaler and our period, so the prescaler determines how much it scales that 100 megahertz clock by in order to trigger each count of the timer. So the timer is basically just a counter that can count up or down. So if we had a prescaler of 4, then effectively it's going to supply the counterpart of the timer with 25 megahertz rather than 100. So it's basically taking the clock and dividing it by the number in the prescaler. So our period is then, say if we had a period of 1,000, then once our timer counter gets to that 1,000, then it's going to trigger our update interrupt. It also will then reload the counter from the auto reload register. In this case, we're just going to basically get it to reload from 0, start counting up again, and then once it reaches the period value again, it'll then trigger another update and keep going. So that's kind of how that works, and we'll get to see that in action as well. So let's pop in some initialization methods for this one. So it's going to return a QA result for that one so that we can find out whether it succeeded or not. And also put in a dinit method for that. We're going to want a handler method, which will be called by the interrupt when it gets triggered. and it will then, depending on what we've supplied for the handler function and handler class, it'll then call those guys as needed. We want some control methods. Might just pop a bit of space in there so we can scroll a bit better. So for these ones, we're going to have a few. So firstly, we want to be able to set what our handler function is, which we will be passing a IRQ handler callback function, which is a pointer to the function as we've defined in our setup file. And this one will be a pointer to a callback class. Also going to want to be able to update the timer mode. So although we will be supplying it with the particular timer mode we want when we hand it the init structure, if we want to change that without having to deinitialize or things like that, then, or destroy and recreate the class, then we can use this method to do that one. And we'll also pop one in so we can actually retrieve that as well. And don't need to pass anything to that one. These won't be returning anything, which is why we're getting the underline on those. We want to be able to set our IRQ counter target again, even though we're supplying that when we give it the initialization structure. If we want to be able to change that without destroying and recreating the class, then we can use this method for that, and we'll also pop one in to be able to retrieve that as well. Don't need to pass that one anything. We might also make one so that we can retrieve what the current IRQ counter value is. And might make one so that we can actually clear the IRQ counter value as well. So just kind of thinking ahead to the ways in which I may want to actually use it. Not super stressed if we don't end up using certain features, because if the compiler sees they're not being used, it's not going to bother putting that code in there anyway, so it's not really going to add overhead for that. I'm also going to make a couple of private initialization methods, and it'll make a little bit of sense why we're doing that as we start to get the code written for all of these methods. Sort of a bit of a common approach to this. I believe we did it this way for the external interrupts as well, and may have also done it this way for some of the stuff in the videos in the Discovering STM32 series as well, which we'll have another video coming out for that one in the next couple of days. Also have the encoder video, I think, coming out on the same day as that one, so get those two done at the same time. So let's get these guys popped into here. Also grab these ones, pop those into here as well. And let's fix the indents on those first up. Didn't spell that right. There we go. Fix that over here as well. All right. here, we'll copy and paste that, and we'll go through, pop these in here so that it knows what these methods belong to. Need to pop that one in there for timer mode as well, because that belongs to the, actually no, that doesn't belong to the class, that was declared outside of the class, so that's fine. Pop one in there. There, that one there, that one there, and we need one for DINIT mode. Alright. Just make sure all of this is nice and consistent with how we've been doing it, so it makes it easy to read the code across the board. I'll even change the name of that one just so it makes a bit more sense. All of those in there. Pop a few spaces down there so that we can scroll a little bit easier. These are private initialization methods. Get the names in there. Do that for the rest of them, and then we can pop some code in there. Counter value. That one there. Definitely the most exciting part of the whole stream. But a little bit of time and neatness now definitely makes life easier later on, so three more to go. And then we can actually get some code in here and start to have a bit of fun with it. And done. And just refuel. Programming without coffee is no fun. Alrighty, so for our initialization, this is where we're going to start to make use of the timer manager that we did in the previous stream. So Qt timer manager, and we're accessing it this way because of the fact that we made it a singleton class. So firstly, we want to find out if the timer that we want to use is actually being used or not already. So basically asking the timer manager whether the timer that we want to use is busy or not. If it is, then we will return a QA error, perf busy. If it's not being used, then we want to go ahead and register it so that the timer manager knows that we want to actually use it. And then we're also passing it the, I'm going to highlight that correctly. We want to tell the timer manager what we're actually using it for. So we're going to tell it that it's in use and that we're using it just as an update interrupt timer. So next we're going to store the result from our peripheral initialization method. And the reason for that is so that if it fails, then we can then tell the timer manager that we no longer need it. Because if it doesn't initialize properly, then something else can potentially come along and use it, or we can then try and redo it, or depending on how we approach that once we go to actually start using them. And then for our deinitialization, we're first going to check if it's not initialized already, then we don't really want to deinitialize it. So do that. If it is initialized, then we will call perf deinit, and we'll tell it that we want to do a full deinitialization of that. And then once that's done, we can let the timer manager know that we no longer need that timer. Like so. That's those two out of the road. Next up, we've got our interrupt handler, which will be called from our handlers file. So first we want to check our flags. And it's quite important for the timers as well, because some of the timers on this particular device do share interrupts. So timer 1 shares interrupts with timers 9, 10, and 11 in various ways, which we went through in the previous stream. So I'm going to check if the interrupt or the update flag has been set. If it has, then we want to process that interrupt. And then depending on which mode it's in, whether we want it to happen continuously or if we just want it to happen multiple times or just a single time, we need to follow the relevant thing there. Now, because we've got 3 members for the enum for the mode, we need to supply a case for all 3 of them. So in the case of continuous, we're not actually going to do anything in this situation because we're just going to let it run, but we are still putting a case in this switch statement for that, just because it will keep the compiler happy. So in the case where we've got it in multiple mode, we will first increment the IRQ counter value, and then we're going to check if the counter value is greater than or equal to our target. Then we will go through and actually stop the timer at that point so that it just gives us the particular amount of interrupts that we want from it. We might also go through and reset the counter value at that point as well. But we might actually do that in the stop method rather than popping it in there. And that's kind of all we're going to need to do for that case. And then in the case where we have timer single, we're just going to call stop because we only want it to happen the once, and then we'll do a break for that one. So that's the switch statement done, and then we're also going to want to call our either our handler function or our handler class, depending on which ones are set up. So either one or both. So if MP handler function, so if it's not null effectively, then we'll go ahead and call that one. And we're not going to be passing anything to that one at the moment. And same thing for our class. If the class isn't null, then we're going to call the handler method of that class. And then finally, we need to clear our update flag so that the time, if we don't do that, effectively we'll exit the IRQ handler and it's going to call it again straight away because the flag's still set. So need to make sure that we actually clear that one. Like so. And that's our handler method done. These guys are fairly simple, so we're just going to go MP handler function equals P handler, and same for this one, will be MP handler class equals P handler. A few more nice simple ones because we're basically just setting or getting values, which is always good. Get these guys out of the road fairly easily. So that will be ME mode equals E mode, and that will be return ME mode. This will be MU RQ counter target equals U counter. Might actually rename that. Don't like that. It should be U target because that's effectively what we're setting there. Make a bit more sense that way. That's better. All right. So for this one, we're just going to be returning MU IRQ counter value. And this one, we just want to clear the IRQ counter value. So IRQ counter value equals 0. Now start and stop methods. So in this case, we first want to check that the timer is initialized and that it's not already started. I'll just do it that way, like so. Alright, so we'll reset the counter value whenever we call start. That kind of makes sense. And then we want to enable the interrupt, which will be the update interrupt. And we also want to enable the timer itself. And just pass it the handle for that one. And then lastly, let it know that it is now active. In the case of stopping it, similar thing. So we want to check that it is initialized and that it is active. All right, and in this case, we want to disable the timer. And disable the interrupt. Like so, and also set our state to inactive. Alright, now for the fun ones. So, first thing we're going to want to do when we go to initialize it is enable the timer clock. And we created a method to do that in the timer manager during the last stream. So that one will be ready timer manager enable clock, and we'll let it know what timer we want to enable the clock for. And then we've got to initialize the timer peripheral itself. There's a few bits we've got to supply for that. First of which will be what instance, which timer specifically we're actually doing, and we can retrieve that from the timer manager as well. So we'll go get instance, supply it with the enum for our peripheral, and set our prescaler, which will determine how quickly the counter in the timer counts. Set our counter mode. So I'm just going to do a simple up counter for this one, because we're basically just getting it to trigger the update interrupt whenever it reaches the period value. You can also do down counting, and then there's also up and down counting as well, where it counts up, gets to the period value, and then counts back down to 0. So there's a few different modes it can be used in there. And the cool thing with the timers is they don't necessarily have to be using the clock to actually trigger them. So in the case of when we're during the next stream, when we do encoders, it's actually using the quadrature signal from the encoder to drive the counter, which is kind of cool. So we want to supply it with the periods. Clock division, which is not going to do too much in this case anyway, but we'll set that just to be consistent. Just tell it div1 for that one. Make sure all of that's nice and neat. We want our repetition counter. Just going to set that to 0. Kind of drives me nuts when these guys aren't all lined up. Can't help myself with that. I do like code to look relatively neat. I have a thing for that. And we just tell it that we want to enable preload for the auto reload register. And then we'll go ahead and get that initialized. So I'm just going to pass it the handle for that one, which has our instance and all the information that we've just supplied. And then if that doesn't return okay, then we want to perform a partial dinit. And then we're going to return QA fail if that's the case, so that we know that the initialization hasn't worked. Losing my voice. We want to go ahead and set up the IRQ. So firstly, we need to retrieve from our timer manager what IRQ is associated with this particular timer for its update IRQ. Again, just tell it what timer we want to retrieve that for. We want to set the priority for that interrupt. which we have stored in IRQ priority, I believe we call it. Where are we? Yep. New IRQ priority. And we want to enable that IRQ. Like so. Now we also want to make sure that we set our state. So at this point it's initialized, but it's inactive. We'll stay inactive until we call start. But its initialization state is initialized at this point. And then if we get to this point, everything's worked, so we can return QA OK. Now for our deinitialization, it's a little bit simpler. So if the mode I hope I spell that correctly and don't put bits where I don't need them. So if we're doing a full deinitialization, then we will also need to disable our IRQ and deinitialize our timer. And this is why we tell it whether or not we're doing a full or a partial deinit. So if we've gotten to this point in the initialization, we've enabled the clock, but we haven't actually successfully initialized the timer base or done the IRQ. So if we're doing a partial deinitialization, we don't need to disable the IRQ, and we don't need to deinitialize the timer peripheral. Whereas if we're doing a full deinitialization, so it's initialized, we've used it, and then we're deinitializing it, then we want to make sure we do those things, which is why we use this deinit mode enum that we've created. Just make sure that everything stays nice and neat and we don't end up with bits and pieces left over where we don't want them. Might help if I put the brackets in the right spots. So at this point we want to disable the timer clock, and again that's something that we can ask the timer manager to do. So that will be disable clock, tell it which timer we want to disable the clock for, and then finally we want to set our states so that we know that we're inactive and that we're no longer initialized. And the reason why we do that is because we may be in a situation where we want to create the class, initialize the timer, use it, deinitialize it, but not destroy the class yet, because we might want to then reinitialize the timer at a later date. So say for example, if we're in a situation where we want to use that same timer temporarily for something else, then we can disable or deinitialize it for this particular class, then reinitialize it to do something else, say to do PWM or an encoder or something temporarily, deinitialize that, and then come back and reinitialize this particular class so that we can then use that timer for this purpose again. So it just provides that extra bit of flexibility. And part of the reason why we actually went through in the last stream and created a dynamic timer manager in the first place, so that way over the course of a particular bit of code running on the microcontroller, we can chop and change things as much as we like, which is something that you can't really do when things are hard-coded. And considering that the timer manager doesn't really add that much overhead to things in the first place, I think it's worth doing it that way. Especially because what we want to be able to do with all of this code as we move forward for all of the devices is to be able to basically develop a cut down OS for all of them. So in the sense of an OS, things need to be done a little bit more dynamically so that different tasks can ask for access to different resources and peripherals and things like that as needed as the OS is running, rather than it being hard-coded just to do a specific job. So that's all of the code that we need for that. Let's make sure that builds, and then let's see what this does. Always got to be at least one error. 14, that's a pretty good effort. Where do we have errors? Some left over from the last stream. Spelling error there. Spelling error there too somewhere. Oh, QAD should be. Beautiful. What have we got going on in here? That should be an S in there. That's better. Didn't actually build this code during the last stream, which is why we're getting a bunch of errors now, but it's always fun. QAD timer unused. Missed that one there for that too. MS should be an S there. Making the same mistakes all over the place. It's brilliant. Okay. Pop a break in there just to keep the compiler happy. And it's going to want me to do that down here as well. And that's all of those. What have we got going on in here? 2 errors. Get rid of the R there. And what do we got here? Aha. Missing a 0 for that one. Missed a return statement somewhere. Which file is that in? It's in our timer manager HPP. That should be returning a value. Is that the only warning? Beautiful. 0 errors, 0 warnings. Let's try this out. We've still got our external interrupt stuff in there from a couple of streams ago. We'll leave that in there for the moment. We are going to firstly include QAD timer.hpp. Might be helpful. And QAD timer. And we'll just call this timer test. Also going to want to supply it with a callback method. And we're going to do the same thing in here as we did with our external interrupt handler. Except we'll just put timer triggered so that we know. There we go. Awesome. Then we can come down and get this guy set up. Okay, pop that in here. So we want timer test. Oh, actually, we're going to need to fill out an init structure first. So we will want QED timer init struct, and let's call it timer test init. And then we'll need to let it know which timer we want to use. We might just use timer 2 for this one. Doesn't really matter which one we pick for this, but timer 2 sounds good, and it is one of the 32-bit timers, so we want to let it know what mode we want. So let's try it with our continuous mode firstly. Might just pop this guy over here so we can sort of see both things at the same time. Excellent. We want our prescaler. And we might make our prescaler for this one 100,000, which means that each counter tick of the timer, given that it's a 1 megahertz, 100 megahertz clock, so that's going to divide it down to, should be 1,000 ticks per second. And if the timer is counting up 1,000 increments a second and we set our period to 1,000, then that means that our update interrupt should trigger once every second. To note here, if we were to use one of the 16-bit timers, we wouldn't be able to give it a value of 100,000 because the highest number that we can fit into 16 bits is 65,535. So that would need to be taken into account. So in that case, I would potentially put, say, 20,000 in as the prescaler and 5,000 as the period, which would still give us a 1 second update. With the main difference being that it's going to then update, count up 5,000 times a second instead of the 100,000 that we're, no, the 1,000 that we're doing now. Coffee's running out, brain's falling asleep. Okay. Our IRQ priority doesn't matter all that much for the moment. We'll go somewhere in between the 0 and 15. So let's just go with, let's go with 9. That sounds good. And then last but not least, we will set our counter target as well, because once we make sure it works continuously, we'll try out the multiple mode as well. So let's pop 6 in there for that one, just a random number. And let's go timer test equals new QED timer, timer test init, like so. And then we're also going to need to initialize that one. Pop that guy back there, give us a bit more space to move. So let's go if timer test init. So if it returns an error, it'll be true. If it returns OK, it'll be false because of how we got the enum set up. So QA-OK is 0, whereas any of the errors are 1 or above. So if it fails, then we will turn on, I believe we've got, that's where our split view comes in handy. Where are we? Okay, it is GPIO user LED. So we'll turn our user LED on if it fails. so. We'll also use our serial to output an error. And if we get to that point, we'll chuck it into an infinite loop so it doesn't continue. Whereas if it succeeds, also want a message sent out to serial to let us know. And then if it succeeded, then we will also go ahead and get that one started. Now, just about ready for that to be tested, but we also need to hook up our interrupt handler as well. It'll be the last thing that we need to do there. So let's jump into our handlers files. And this will be timer2 IRQ handler. Copy that one, just save that, pop this into here. And this will also need access to our timer file and also to our class so that it can call the handler for that one. Like so. Make sure that all of that builds okay. Wonderful. All right. So let's get that popped over onto our Nucleo device. Never a fan of that particular error. Okay, let's have a look at what's going on there. Typically, the way I would solve this particular issue is by restarting the computer. However, I don't really want to do that during the same stream where I want to actually demonstrate what it should be doing. So okay, why don't we jump back to that one, and that wasn't what I wanted. Let's see if we can get around that by jumping into our release config. Still going to give us the same error. All right, plan B. Let's just get rid of that. Get rid of that. Also get rid of that. Let's see if that will give us a bit better luck. How about that? I bet it was the antivirus. Thank you to the person that popped that on the ST. Oh no, it's on Stack Overflow. So BizHoy on Stack Overflow with that one came in for the win. Wonderful. Love it. Would have annoyed me if I couldn't demonstrate this during the same stream and had to restart the computer. So learned something, and we'll remember that for next time. So anyone who comes across that particular error, you can either restart your computer, which is what I would do normally, and generally it would work fine after that. However, if you're running antivirus, get rid of it. Get rid of anything else that you're running that you don't need to be running. And it should potentially work at that point. Now, let's just reset this guy. So our timer is initializing correctly, and our external interrupt is still working, but we're not getting our timer interrupt triggering. So let's figure out why that is. So that is correct. Pretty sure that is the name it definitely needs to have. Yep, time to IRQ handler. Timer test handler, so we're calling that one correctly. And we are getting the flashing LED, so we know it's not getting stuck inside a handler. We're not getting stuck inside the interrupt because we know that we can still trigger the external interrupt, which has a higher priority, I believe. Which it does, because we've set A as, we're using the same priority as our UART, which we might decrease the priority on that one. I don't think that's why it's happening though. Let's have a look in here. We know that we're initializing properly, so all of that's got to be occurring correctly. So a couple of things to check. I want to check if we're actually getting to that point. And pop a breakpoint in there as well. As we'll go in and we'll actually see how the peripheral's set up at that point, whether there is actually any issues occurring or anything that we've missed. So I'll switch to that perspective. I'll run to that breakpoint. So at this point we should be... It hasn't actually set initialized yet. Got the correct IRQ. Let's check our reset and clock control. Let's jump forward a bit more. We are actually getting to our handler, so this is actually being triggered. So let's just step through this. Okay, it's doing that correctly. What's our... Aha! We did skip something, and I think I'm almost getting really good in these videos of making silly mistakes. But again, you get to see how the debugger works, so I don't necessarily see that as a bad thing. What do we call it? Timer test handler. We're not actually setting our handler, which definitely is a helpful thing to be doing. So set that one in there. We will remove those breakpoints we popped in there. Breakpoints and the debugger, super useful, along with printing stuff to serial so that we can see what's going on. Also useful. User LEDs, also super useful. Use as many debugging tools to find out why something's misbehaving as possible, because it will definitely make life a lot easier for you. So let's dump that onto the device, assuming that will compile fine because we didn't change much. And we have it triggering. Seems slightly fast for what we want though. Let's change that to 2000 and see what that does. Just clear that. It's too fast still. That's half a second. Random. Let's try that. If we were getting half a second, this should give us 1 second. Okay, what we might do, let's change this to 20,000. And we'll change that to 5,000. So I'm wondering if it's an issue with 16-bit value, or the timer not operating in 32-bit mode or something like that. It is. So for some reason, it was not letting us use 100,000 in here. So it was overflowing a 16-bit value somewhere, which is funny because timer 2 is a 32-bit timer. We'll go with that for the moment, but that gives me something to investigate a little bit later. Let's try our multiple mode. We'll make sure that works, and this should give us 6 interrupts triggered, and then it should stop because we've supplied it with a counter target. So we'll test that and make sure that that works correctly as well. Triggered 6 times and stopped. And if we reset the device again, wonderful. Like a charm. Happy with that. So that is how to do update interrupts for timers. As I mentioned a couple of times, the next stream for our STM32 basics will be using timers for working with rotary encoders. So like these sort of things. Let's use this camera for that one. So I'll be hooking up these rotary encoders like so. They're just the standard ones that you can get off eBay, which is where I got these guys from. Some of them are more reliable than others. I think I got a batch of 10 of them quite a while ago, and at least 2 or 3 of them were a little bit flaky. Sometimes they don't register which direction you're turning them in correctly. So just be aware of that. If you're going to buy the cheaper ones, you might get a couple of crappy ones. So considering they're only like $1 or 2 Australian each, not a bad idea to get a handful of them. I normally do that with a lot of the components I buy. Get a few at a time. That way, if one of them is a little bit faulty, I don't tend to worry about it too much. After that, we will be doing another STM32 basics video where we use timers for pulse width modulation, as I mentioned. So we'll be hooking up some LEDs and getting those working. There's also another video coming out for our Discovering STM32 series as well, which will be out in a couple of days, where we get a bit more of the rendering code done for the LCD screen for our STM32 F7 Discovery board. So plenty more videos coming out. I'm hoping to get maybe 2 to 4 more videos done this week, but there is already another 7 videos which I've completed the prep work for, so they'll be coming out shortly. And my list at the moment of potential future videos is well over a couple of hundred at this point. So there's a lot of content to come, and I do want to try and get regular content out with multiple videos per week. So the no videos last week was only because I was sick. I really want to try and get them coming out regularly, so I do quite enjoy doing it. But if you have liked this, if you found it interesting, definitely would love it if you followed us on Twitch or liked and subscribed on YouTube. If you've got any questions, would like to ask about what we've done in this video or other videos, or if you'd like us to answer questions or cover something in a bit more depth, definitely leave a comment for us. You can also jump on our subreddit, which is r/ones and zeros. I do keep an eye on that one. I'm also posting the new videos and things up there as well. So definitely happy for people to jump on there and ask questions. And we also have an email address if you'd prefer to do things that way, which is contact.onesandzeros@gmail.com, which will come up on the end page in a moment as well. And thank you so much for watching. So whether it's daytime, nighttime, whatever it is where you are in the world, I hope you have a wonderful day. It's currently 1:30 in the morning here. Thanks for watching.